let's get into SASPIF and apply the technique of principal component regression. To do this, we're going to use some data from baseball. It's from 1987, and we have a number of attributes about each player, being the number of at-bats, number of hits, home runs. We also have career information, so career at-bats, career hits, career home runs. Some information about defense, putouts, assists, errors. The goal for this data is to predict their salary. I'm sorry, so the data is from 1986 and we're trying to predict the 87 salary. To do principal component regression, we're going to use PROC-PLS. Now we could just use PROC-REG and put in the principal components that we compute from PROC-PRINCOMP. The reason I'm using PROC-PLS is because it will do that solution math, substitution math for us. It will also do the cross-validation for us. So when I put the method as PCR, that specifies, just put principal components into regression. I can then ask for some cross-validation. I want the data divided randomly into 10 folds, and I'm specifying a seed so that the output that you see will be the same as mine. There's class variables that are league and division, and I put all the variables into a model to predict salary. The first graph you'll see in the output is the cross-validation result. It selects 4 components to minimize out-of-sample error. So this is like the answer to the cross-validation. 4 components is best. On the top, you can see that with 4 components, the average error for cross-validation was less than 0.9. That top line is showing us the average root mean predicted residual error sums of squares. So SAS is the only place I've ever seen this acronym PRESS for predicted residual error sums of squares. It's just RMSE on that out of sample data, so the average across the folds. Down at the bottom, I have information about R squared. The top, or the green line, is the percent of variation in X. All right, so that's in all the X's. That's the percent of variance explained in my data by my principal components. On the bottom is the R squared from the regression model, where I put the principal components to predict Y. So this brownish line is the one that you're most used to associating with the word R squared. This green, we previously called that the percent of variation explained by our principal components. So you can see, even at 2 factors, the benefit to R squared drops off considerably for the addition of extra factors. You could make an argument for choosing 2 components here because it does not look like 4 components is substantially better than 2 components. And the error actually increases when you put in 3, which may lead you to believe that this is a turning point at 2. The next piece of output is this correlation loading plot. There's a lot of information on this plot, so I'm going to try to take you through it little by little. The axes here represent the first and second principal components. Now you notice these are called the factors. I had some students tell me they were confused about the difference between factors and components. Now, this helps make my point that you should be confused because there's not much difference. A component can be thought of as a factor. It's just often not a particularly useful one for telling a story, and so we rotate it so that we can tell a better story about it. Also on the X and Y axis, you're shown the XR squared and the YR squared. Again, the XR squared is referring to the percent of variance that's explained by this PC. That's the total variance in the X variables, right? This is percent of variance explained in terms of principal components analysis. That YR squared refers to the R squared for predicting the target with just this principal component. So this is a traditional proc reg R squared. So what's kind of interesting is that when you add in factor 2, your addition to the R squared is in the second decimal point. YR squared for factor 2 alone is actually 0. But you do explain considerably more variability in the X data. All the observations are here in the middle, so you can just notice any observations that are extreme on either component. And so there are only 3 here that seem to separate away from the data enough even to read their labels, but nothing looks too extreme. The XY coordinates of each of these variables here give the correlation of each variable with each of the principal components. So for instance, career home runs has a correlation of 0.75 with the first principal component and a negative correlation with the second principal component. Now this is actually a good place to point out that for correlation PCA, the loadings actually do represent correlations of the variables with the principal components. That is only true for correlation PCA. The radial coordinate here tells us the variable's communality. This is the R squared for predicting the variable using the 2 principal components. So the farther away each of these variables is from the center, the more it's represented on the first and second principal component. So the information from at-bat runs, RBI, career home runs, years, looks like career at-bats, all of these variables that are, farther away from the center are all well represented on the first 2 principal components. Whereas these defensive variables, errors, assists, putouts, and the league that the individual is in, none of those variables are very well represented on the first 2 components. Now, this correlation loading plot does not give you all of the information from even our model, our principal component regression model, right? This only tells you about the first 2 components. Why? Because it's the only 2 dimensions that, we can only plot in 2 dimensions. So it makes sense to show the first 2 because they have the most variance. But we saw from that cross-validation plot that the selected number of components was 4. So to finalize the model, we're just going to run this model on all of the data, specifying that that number of components to be 4. If we add the solution option on the model statement, that will give us the parameters in terms of the original variables. So when I provide that solution option, I get this final table of parameter estimates. Now that's all that comes out. I don't get any of the hypothesis test information or standard errors. Because I have introduced bias into the model, I know from the theory that I should get a large reduction in the variability of these estimates, but I cannot tell you anything about the distribution of the null hypothesis. Now, the point I like to make about this is, students sometimes get bent out of shape when they learn that they can't do hypothesis testing. And what I want you to keep in mind is that these techniques, we're trying to solve severe multicollinearity. if I have severe collinearity in my data, would it really make sense to try to do hypothesis testing to try to tease out how much of someone's salary is due to home runs this year versus, say, hits this year, or career home runs versus home runs this year? These variables are so highly correlated that you can't really tease out the effect of one versus another. So overall, our goal is to kind of take advantage of that collinearity and make a good prediction with fewer variables.